Hello my dear students, welcome to Deeksha Karnataka, and in Masterstroke today I am going to discuss a very important chapter, ray optics. So if you are a second PU student preparing for your PUC exam, or you are just a dropper, or you are doing both KCET as well as PUC, then definitely this chapter is very important for your preparation. Now today I am going to discuss all the concepts in detail about ray optics. So you may have studied the chapter briefly, but you have forgotten some concepts. Some concepts students don't study properly, that also I will discuss in today's lecture. So all the concepts, all the doubts that you have, you can ask me in the comment section below, and anytime I get time I will definitely try to answer all of your queries, right? So let us start. First we will look what we are going to cover in today's lecture. Obviously, as usual, reflection and spherical mirrors. So law of reflection, spherical mirrors, a mirror equation, refraction and Snell's law, obviously very important. Total internal reflection, one of the most important concept. Lenses, from there you can expect at least one numerical question in your PUC exam. Okay, this year we are expecting a numerical question from this chapter rather than a theory question. So lenses is very important for PUC as well as in KCET. Why? Because from lenses questions are very common in KCET exam. Microscopes and telescopes. Students generally ignore microscope and telescopes while preparing for PUC, but in KCET microscope and telescopes are important. Also in PUC exam we have seen MCQs and fill in the blanks coming from these two concepts, so you cannot ignore these concepts for your PUC preparation as well. And microscope and telescope, even though they are very easy concepts, sometimes students make mistakes on their magnification and minimum distance of distinct vision. So you have studied that in your class 10, so let us refresh everything today in this lecture. So first we will start with reflection. What is reflection? Reflection is very simple. A ray of light falling on a medium, and after it falls on that medium it reflects back. Reflects back means it is bouncing off a surface. Okay, bouncing off, like if you take a ball, throw on the surface, it will bounce back. So that is called reflection. Now bouncing is slightly different than reflection because bouncing can be controlled by using spin or using certain surfaces, but reflection always obeys two laws. Okay, reflection means ray of light falling on a surface, bouncing off the surface, but it always obeys two laws. What are those two laws? First law is angle of reflection equals to angle of incidence. So if you see in this diagram, this is the angle of incidence, this is the angle of reflection, and they should be equals. So theta I should be equals to theta R. Next is the incident ray, reflected ray, and the normal to the reflecting surface at the point of incidence lie in the same plane. So basically this ray and the normal on the point of reflection, they all will lie on the same plane. That means this is a single plane. This entire thing is a single plane. Now in 2 dimension you might think, okay, it might be very simple, but in 3 dimensional when you think it's still a plane. Now one more important thing is the angle of deviation. So when there is a mirror involved over here, a ray of light is falling, and after reflection it goes to the certain angle. So angle of incidence say I, angle of reflection say R. Now I equals to R, obviously. Now if there was no mirror present, then the ray would have traveled in the straight path, right? So that is the major concept of ray optics. Light is traveling in a straight line. We are not considering any other method. So when the light is traveling in a straight line, the angle between the incident ray and the reflected ray is called angle of deviation. So by the angle it deviates from its original path. Now what is this angle of deviation? Very simple, 180 degrees minus 2i. 180 degrees minus 2i. Now angle of deviation does not depend if there is a glass slab present over here or a water slab present over here. As long as a deflection is happening, this law will still be valid. So there was a question in the past where there was a glass slab is given, and it was said the ray is falling with some angle, then what will be the angle of deviation? Even if there is a glass slab, if there is a reflection, only the angle with the first surface is considered, and the angle of incidence with the first surface is considered. Okay, nothing else you need to worry about. So only the angle with the first surface and no matter if it is partial refraction and then it is coming back reflecting back, so angle of deviation will be same, right? So remember this concept. Next is spherical mirrors. Spherical mirrors is basically a part of sphere with one side silvered. Okay, so it's a part of a sphere. So if you construct a sphere like as if is a football. Okay, football is an example of sphere. Even your cricket ball, tennis ball that you play is also a football, is a sphere, sorry. This is also a sphere, but that size is small. So if you take a large sphere, okay, like a globe is also a sphere. So if you take a large sphere and cut it and partially silver one side, then that is called a spherical mirror. Now based on which side you are silvering, there are two types of mirrors. Okay, convex mirror forms only virtual and diminished images. What is a convex mirror? So if you suppose the reflecting surface is this one, so the outer bulged out surface, this is called bulged out surface. So you have silvered this side, okay, and you are allowing the ray of light to fall in this side, then this is a convex mirror. Vex means bulged out. Okay, and next is concave mirror. What is a concave mirror? Concave mirror is obviously it is like a caved in. Okay, it is a caved in surface, it is a bulged out surface, ray of light falling from here. Okay, so basically if you flip a convex mirror, you get a concave mirror, right? So basically they are opposite of each other, but based on the reflecting surface you can say this is a convex mirror, this is a concave mirror. Now convex mirror are simple, they forms only virtual and diminished images, whereas concave mirror forms real and virtual images both. It can form either virtual image or real image depending upon the position of the object. Okay, for object distance greater than focal length, for object distance greater than focal length, it forms real images only. For object distances less than focal length, it can form virtual and enlarged images. Okay, and now based on their properties, there are multiple application of them. First of all, concave mirror are used in solar cooker. As you can see, this is a solar cooker. All the ray of light falling on this concave mirror, they are being focused over here, and here you have the cooking utensil which collects the heat and then it's heated up the food inside. Okay, this is a very basic design of a solar cooker. Next, convex mirror are used in side view mirror or rear view mirrors. Okay, why it is so? Because of its concave nature, it has a larger field of view, so you can see a large portion behind you, and that's how you can see, okay, a car is coming or someone is coming from behind, or if I want to cross on this side, if there is a vehicle moving from this side or not. So that is a very, very essential application of convex mirror as well. Concave mirror, one more application was there. Right now we do not use it, but in ancient time, when makeup mirror, that is when you are seeing yourself in front of a mirror, okay, they used to be a concave mirror. Okay, because the face appears little bit bigger. So all the previous generation queens, princess, they used to use concave mirrors for their makeups. Okay, nowadays all the beauty parlors, etc., if you are visiting somewhere, okay, they use plain mirrors only. No concave mirror is used. Now let's move on to sign convention. Sign convention for mirrors and lenses are same. So we will teach it only once. Okay, but if they ask you what is the sign convention for lenses, it is same. Now very basic and important thing you have to remember, you have to go back to your old coordinate system. Okay, we have all learned about coordinate system. So here is a y-axis, here is our x-axis, right? And what is here? Here we have negative x-axis, here we have negative y-axis, right? So any distance is measured in the positive x-axis direction, okay, that is always positive. Any distance is measured in the negative x-axis direction is always negative. As simple as that. Any direction along positive y-axis is positive, any distance along the negative y-axis is negative. So this is called Cartesian sign convention, because this system is Cartesian system, Cartesian coordinates. Okay, Cartesian is the person who developed this coordinate system, and that's why it is called Cartesian sign convention. So any distances along positive x-axis is positive, any distances along negative x-axis is negative. So don't try to remember opposite to the direction of ray, in the direction of ray. Don't worry, don't think about that too much. Only thing you have to remember is anything in the positive x-axis is positive, anything in the negative x-axis is negative, anything in the positive y-axis is positive, anything in the negative y-axis is negative. That's it. And your mirror or lens is located at the origin. Okay, mirror or lens is located at the origin. Okay, origin is your location of your mirror and lenses. Now to use this sign convention, you have to remember that objects are always in the left hand side. Okay, objects are always in the left hand side. So object distance by default is always negative. Object distance by default is always negative. So why we need to know this sign convention? Because based on the sign convention, the value will change. If you make a small mistake in plus and minus, your entire answer will be different and you will get what? A big 0. Okay, so remember that object distances are always negative, object height is always positive. Objects are always in this orientation. Okay, so object heights are always positive, object distance is always negative. So based on the final image position, it can be image distance can be positive or negative based on its location. Similarly, image height can be positive or negative based on its location. So you have to, whenever you are using a mirror equation, magnification equation, whenever you are using an equation, you have to be careful about the sign convention. U by default is negative. Focal length based on different condition can be positive, can be negative as well. We will see that in a while. Now, when solving problem, object distance is always negative. As I mentioned, image distances can be negative or positive. Focal length, concave mirror or concave lens is always negative. So if you read concave, you should remember focal length is negative. Okay, if you read convex, lens or mirror does not matter, focal length will be always positive. Okay, convex lens, convex mirror, focal length positive, concave mirror, concave lens, focal length is negative. Does not matter. Focal length definition, what is focal length, by the way? So we are giving in terms of mirror only. So suppose we have a mirror, okay, a parallel ray of light falls on this mirror. Okay, parallel ray to the principal axis falls on the mirror, then they all merge at a single point. That is called focal length. Okay, that is called focus of the mirror, and the distance is called focal length. It is denoted by a symbol small f. Focal length is denoted by a symbol small f. For lenses, parallel ray of light falling on it, when they converge at some place, okay, or appears to diverge from some place, that is called focal length. Okay, so parallel ray falling on a mirror or lens. Parallel ray falling on a mirror or lens is basically the definition of focal length. Remember, ray has to be parallel. Conversely, if you put an object over here, a ray of light over here, then after falling on the mirror, it will become parallel. It will exit parallel. Okay. Now, principal focus, secondary focus, and not principal focus, these are other concepts that is not required to study. So basically you have to remember two things. First of all, object distance is negative. If it is concave, it is negative. If it is convex, it is positive for focal length. Okay, so these points are very, very important, and image distance will come from the formula. So what is the formula? So mirror equation formula is 1 by V plus 1 by U equals to 1 by F or equals to 2 by R. So from there we can also say that focal length is actually R by 2 for a spherical mirror. Okay, so it is the focal length equals to R by 2. The derivation I have done in my Brahmastra series. You can go and check that out. Ray optics Brahmastra, you can search. There I have done this derivation. It's important derivation for your PUC exam. Now, why I have written in your most of the textbook, it is written 1 by U plus 1 by V. But why I have written 1 by V? Because to make sure that you don't forget, in lenses 1 by V minus 1 by U, for mirrors 1 by V plus 1 by U. Okay, and the right hand side is same. Now in case of magnification, In case of magnification, m is given by minus v by u. Why magnification is important? Suppose you have a small object, you want to magnify it. That means the image should be bigger in size. Or you have a bigger object, you want to make it smaller in size. So based on this magnification, you can find the size. For normal plane mirror, magnification is 1. So whatever is the size of the object, you see the exact same size of the image as well. Okay, now in both cases you have to apply the sign convention. You have to apply the sign convention, and these two formulas are valid for all cases, all position of the object. Only thing you have to be careful, you must use new Cartesian sign convention, the sign convention we have learned. Okay, so in case of magnification also you have to use sign convention, right? Now let's move on to a question. A point object is moving uniformly towards the pole of a concave mirror. The focal length 25 cm along its axis as shown below. The speed of the object is 1 meter per second at time t equals to 0. The distance of the object from the mirror is 50 cm. The average velocity of the image formed by the mirror between time t equals to 0 and t equals to 0.1 second is. Okay. So you have to find the average velocity of the image. So very interesting question, sir. This is a lens equation. Why they are bringing in the velocity? Okay, you might ask it, but okay, it is solvable question. I think it came in 2023 in KCET. So here is an object. Okay, at t equals to 0. At t equals to 0, the object was here. Okay, and if you see that the focal length was 25 centimeter. The focal length was 25 centimeter. And for this particular chapter, the unit conversion is generally not required except when you are calculating power. Okay, for power it has to be converted into meters. Otherwise, unit conversion is not required. Only way you need to convert the units, if something is given in centimeter, another one is given in millimeters. Otherwise, you don't need to convert the units. Centimeter you can keep it on centimeter. Okay, I will explain where you have to change the sign. Now. So initially the object was at a 50 centimeter distance. So if you see, this is focal length f, then 50 centimeter is nothing but the radius of curvature. Okay, the 50 centimeter is a radius of curvature distance, right? F is equal to r by 2. Now that means the object was located at radius of curvature. Now if you go back to your class 10th knowledge, you know that if an object is kept at a distance 2f or at a distance radius of curvature, if you keep an object here, the object will form an image exactly at that same position. Okay, the object will form an image exactly at the same position. So in this case, the object is moving with the velocity say x meter per second. The image will also be having the same velocity x meter per second. Okay, so object will also object and image both will have same velocity, because at this point both are having same position. Now as the object is moving, image is also moving, but based on their final position we can find what is the final velocity. Okay, let's start. We have to find where the object will land after 0.25 second. Okay, after 0.25 second, where is the object? The speed of the object is 1 meter per second. So speed of the object is 1 meter per second or 100 centimeter per second. As I mentioned here, because it is given in meter per second, we have to convert it back to centimeter. So it is a case where meter is being converted into centimeter, not the other way around. Okay, so V is 100 centimeter. So it is after 0.25 second. What is the displacement? Suppose the displacement of the object say is given by d. Displacement of the object is given by d. Then what is that d? So d equals to Vt. S equals to Vt. So d equals to Vt. So simple, very simple calculation. So 100 into 0.25, that is 25 centimeter. So the object moved towards the mirror by a distance 25 centimeter. Okay, this is mentioned that object is moving with a speed of 1 meter per second towards the mirror. Okay. uniformly towards the mirror. Okay, so towards the mirror is mentioned. Now, so object moved by a distance 25 centimeter. Initial distance was 50 centimeters. So what is the new distance? New distance is 50 minus 25, that is 25 centimeter. So object is at a distance from the mirror at a 25 centimeter distance. So 25 centimeter distance means where is the object now? The object is exactly at focus. The object is exactly at its focus. So object reached its focus starting from 2F. Okay, so when the object is at focus, where will the image be formed? So when an object is kept exactly on the focus, the image formed exactly at infinity. So the image will be forming at infinity. So U is 25 centimeter means V must be infinity. You can use mirror equation, but not required. We know this from the knowledge that if the object is kept at focus, the image is basically formed at infinity. So object is at 25 centimeters, so image will be at infinity. So when the image is at infinity, then what is the displacement of the image? Image started from 50 centimeter, and moved to infinity in 0.25 second. Okay, so that is how we calculate the average speed. Okay, in JEE level they will not give you this simple question. In JEE level they will give you some value which you can you have to actually calculate the distance. In this case it is not required because the displacement of the object is infinity minus 50, which is equals to again infinity. So the displacement of the image say di equals to infinity final position minus 50 initial position, and infinity minus anything is still infinity. So the speed of the object is divided by the time, which is 0.25. So infinity divided by any finite number is still infinity. So the speed of the image will be infinity. Speed of the image will be infinity. Suddenly from 2F it moves to infinity. That's why its speed is infinity. Okay, very interesting question. You don't need to do a lot of mathematics over here, but if you understand that the displacement is 25 centimeter, that means it moved from 2F to F. The image moved from 2F to infinity. Okay, so that is the main logic of this question. So speed of the object will be infinity. Now if you want to practice more such questions that we are solving over here, then obviously ABHYAS KCET test series is already there live for all of you to purchase, and here you will get 35 KCET, exactly KCET level questions to prepare yourself better for KCET exam. And absolutely free of cost, you are getting KCET chapter wise last 10 years PYQs, and for that you don't have to pay anything extra. The price is same as last year's. Okay, but we have added chapter wise KCET 10 years PYQs in the form of quiz. It will not just a simple PDF where you will get the questions and solution. It will be in the form of quiz, so you can test your knowledge, okay, whether you are able to solve those questions in the quiz format or not. Okay, and the question papers are exactly like KCET level. So if you are preparing for KCET, the time management etc. is very, very important, and KCET level question practice is very, very important. It should not be too difficult, it should not be too easy. The level should be exactly of KCET, right? So here we are going to give you 35 tests which are exactly of KCET level, and also you are going to get physics, chemistry and biology covered in all subjects, right? Now let's continue. The price of that is obviously 1499. If you want to purchase it, the link of this is given in the description. So don't wait, already more than 1000 students have already registered for our ABHYAS, and the number is growing every day. Latest figure I don't even know right now, so don't wait, right? Because 1000 crossed a few weeks back, so right now maybe it is 1500, I am not sure. Anyway, if you are still waiting, don't forget to purchase it from the link given in the description. Now let's continue. Laws of refraction, another important concept. The incident ray, the refracted ray and normal at the interface of the point of incidence all are in the same plane. So what is refraction, by the way? So refraction is when a ray of light falls on a certain medium, part of it bounces back, that is law of reflection, we know that, but part of this light goes straight into the second medium. Okay, so light ray actually, instead of bouncing back, some part of the ray slightly bends and move in the second medium. This phenomena is called refraction. Refraction we observe every time, right? Refraction is very, very common phenomena. Now so basically this law is same as the this law is same as the law of reflection. So incident ray, refracted ray, this is called refracted ray. The ray which travels into the second medium is called refracted ray. So incident ray, refracted ray, and the normal drawn on the point of refraction, they all lie on the same plane. This white screen over here represents the plane. Snell's law here, I is not equals to R, but it's slightly complicated. So Snell is a person who discovered this. The ratio of sine of the angle of incidence to the sine of the angle of refraction is constant. Remember that the angles of incident I and refraction are the angles that incident and its refracted ray makes with the normal. So this is angle of incidence, this is angle of refraction. Both angles are always measured from the normal, not with the surface. No angle, not in reflection, not in refraction, angles are always measured from normal, not from the surface itself. Okay, so this is the angle of incidence, then this will be the angle of refraction. And from Snell's law, sin I by sin R is a constant, and that constant we are denoting it by n to 1. What is n to 1? So sin I by sin R is equal to n to 1. Here n to 1 is called the refractive index of the second medium with respect to the first medium. Okay, so what is refractive index? Refractive index is a quality of a particular medium. If n2 is greater than 1, then R is less than I, that is the refracted ray bend towards the normal. So if the second medium where the light is going is denser, optically denser compared to the first medium, then the light ray bend towards the normal. So when the ray of light, suppose this is air, suppose this is water. Okay, ray of light travels from here. When light from air travels into water, it bends towards the normal. So angle of refraction is slightly smaller than angle of incidence, right? So this is I, this is R, so I is greater than R, okay, or R is less than I. On the other hand, if n21 is less than 1, for example, light is traveling from water to air, or for example light is traveling from water to glass to water. Suppose we have a glass kept on top of water. Okay, so in that case glass the density of glass is more than that of water, so light ray will bend away from the normal. So that means, suppose this is say water, this is air. So in this case what happens, light ray bends away from the normal. Okay, so the angle of incidence and angle of refraction, so R increases, R is more than I. Okay, this is the case when incident ray is in a denser medium refracts into a rarer medium. Okay, so denser here, density means optical density, and optical density is the is measured using this value. Okay. Now general form of Snell's law is also very important. Many problems, numericals you need to use. N1 sin I equals to N2 sin R. Okay, suppose the refractive index of this medium is N1, refractive index of this medium is N2. Okay, this is I, this is R, then N1 sin I equals to N2 sin R. Okay, because in many cases you will find yourself that when you are solving a question where a glass slab is immersed into a water. Okay, so the outside medium is water, inside medium is glass. So how to use Snell's law? So you can use this shortcut. No complication, only N1 sin I equals to N2 sin R. Now refractive index is dependent on the wavelength of light. So the color of light, basically the color that you are using. Okay, so refractive index is inversely proportional to wavelength of light. Refractive index for violet light is more compared to that of red. So red basically scattered less because its refractive index is less. Okay, that's why scattering is also less. Scattering also depends on wavelength, and if you apply the same logic in case of say a prism. Okay, if you see that the red light diffracts the less, whereas the violet light diffracts the more. Why so? Because red light has a very less refractive index compared to violet. Also, the refractive index is dependent on the speed of light of the medium. So relationship between refractive index and speed of light is C by V. This is called absolute refractive index. Absolute refractive index means refractive index with respect to free space or vacuum or air. Okay, for our most common cases we will take air, because refractive index is air with respect to vacuum is almost 1.002. So that can be approximately taken as 1. So refractive index of air is also 1. Okay, so normally speed of light, refractive index is speed of light in air or divided by speed of light in medium. Okay, and in terms of relative permeability and permittivity, it is mu r equal into epsilon r square root. Okay, 1 by mu naught epsilon r is the refractive speed of light in vacuum. If you remember, in electromagnetic waves chapter we have discussed it. So mu square root of mu r into epsilon r is the refractive index for a medium. And relative refractive index is given by the simply speed of light, so v1 by v2. Okay, or it is also written as n2 by n1. So refractive index of the second medium with respect to first medium is absolute refractive index of the second medium divided by absolute refractive index of the first medium. Let's solve one question. The refractive indices of glass and quartz with respect to air are 3 by 2 and 12 by 5 respectively. The refractive index of quartz with respect to glass. So refractive index of glass is given by 3 by 2. With respect to air means absolute refractive index, and refractive index of quartz is 12 by 15. So refractive index of quartz NQ divided by NG will be equals to 12 by not 15, sorry, 12 by 5, 12 by 5 divided by 3 by 2. So it will be 12 by 5 into 2 by 3. So 4, so it will be 8 by 5. So refractive index of quartz is 8 by 5. So correct answer is option A. Now let's move on to total internal reflection. Total internal reflection is another very important concept. When light travels from an optically denser medium, that means for example water, to a rarer medium, for example air, at the interface for certain angle of incidence, the refracted ray of light passes exactly between the planes separating the two medium. Hence the angle of refraction in this case is 90 degrees. Okay, this angle of incidence is called critical angle. I will explain. Don't worry. Suppose we have for this purpose we are drawing it like this. Suppose we have water over here and we have air over here. A ray of light which is traveling from here, okay, because it's a denser medium, this is a rarer medium, light ray after traveling up to this point, it will move away from the normal. It will move away from the normal. Now if you increase the angle of incidence, say at certain angle, okay, if you increase the angle of incidence, then what happens? Let me change the color. So if you increase the angle of incidence, what happens is that the ray after passing over here, it travels exactly between the planes separating the two mediums. So as you are increasing the incident angle, the ray is bending, and then it's straight away moving between the planes separating the medium. So this angle is called critical angle. Okay, critical angle is represented by theta c or IC. Okay, so this angle is IC. We are not interested in any other angle, but it is just for explanation. So this angle is called IC. Okay, now what will happen if you still increase the angle of incidence? If you still increase the angle of incidence, okay, let me use another color. So this one. So if you increase the ray of angle even further, the ray of light will come back to the first medium and it will obey the law of reflection as usual. And this phenomena is called total internal reflection. When the angle of incidence is greater than the critical angle, the incident light, instead of refracting to the second medium, reflects back to the first medium, and that is called total internal reflection. Here are the few examples of total internal reflection. So if you see one object is over here, there is a prism, and after falling on this prism, the ray of light is totally internally reflected. Here also the ray of light totally internally reflected. This is happening twice, and here also the ray of light totally internally reflected. Based on different application, we use this method. For example, this one is used in periscopes. Periscope is the instrument which we use to observe objects which are at very far. Okay. Now, refraction at a spherical surface. One more important thing that I forgot to mention, that there are two conditions of total internal reflection. First of all, light ray must travel from denser to rarer, and secondly, the angle of incidence must be greater than the critical angle. So if these two conditions are satisfied, then the total internal reflection will be observed. And one more thing, that the application of total internal reflection, there are a lot of applications. One of them is optical fibers. Okay, optical fibers are those cables which is basically responsible for you to observe me right now. Okay, the data which is being transferred from YouTube to your home, okay, that is basically done by optical fiber cables. Okay, in between also, if you are watching something which is suppose you are watching Netflix, or suppose you are watching some Amazon Prime Video or some other channels, okay, Crunchyroll, you are watching Demon Slayer latest episode. So they are basically, the server is located outside India, and from there it is being transmitted through optical fiber cables through some local network in India, and from there it is basically transmitted to your home. Okay, without optical fiber cable, a lot of things are not possible, and communication is one of them, data transfer is another one of them. Right, now let's move on to the next part, refraction at a spherical surface. Okay, so here we have a spherical surface. Now this is a solid spherical surface, unlike the mirror. Okay, it is a solid spherical surface. So this is a part of the sphere. Entire part is basically a curved glass. Suppose this is a curved glass, you have a glass piece like this, and what you have decided, okay, I don't want this glass piece. What I will do, I will prepare a curved glass out of it. So when you curve one side of this glass, this is called a spherical surface. Okay, so it does not require you to be this straight lines are no longer required, so you get a curved surface. So basically you are taking a glass piece and then you polish it from one side so that you get this kind of structure. This is called a spherical surface. Basically, if you construct, extend it, extrapolate it, you will get a sphere. Okay, that's it. It does not necessarily to be a complete sphere, it can be a small portion as well. So when the light ray is traveling in such a medium, okay, the object distance u and the image distance v is related through this formula. N2 by v minus N1 by u equals to N2 by N1 by R. R is the radius of curvature of the sphere. Now how to remember? This formula can be tricky for many of you to remember. Okay, so that's why I say that remember basic length equation. Basic length equation, even though we have not done, but most of you know 1 by v minus 1 by u equals to 1 by f. That is the basic length equation. Right, for this spherical surface, focal length does not matter. There is no focal length for a spherically curved surface. Okay, but where is V located? V is located inside the second medium. So V is located inside the glass medium. What is the refractive index of that medium? Refractive index is N2. So you just need to put N2 on top of it. Where U is located? U is located in the first medium, air. So U is located exactly on top of first medium. So you just need to put N1 over here. Okay, now next what? So you got, obviously there is no focal length, so what you have to write on the right hand side, N2 minus N1, N2 minus N1 divided by only quantity that you have in this case is radius of curvature. So N2 minus N1 divided by radius of curvature basically gives you this equation. So if you remember this thing, you can answer any question that is coming from this formula. Okay, this formula is, do not ignore this formula. This formula is also important for PUC as well as KCET, right? Now, lens maker's formula, another very, very important formula for you. And if you are practicing any derivation from this chapter, then this derivation is compulsory, even though as I am saying that from this chapter we are expecting a numerical question, not a theoretical question. But in case they change the paper at the last moment, then this derivation can come. Okay, so board exam generally they prepare 1 or 2 papers, 1 or 2 different sets of papers, and based on lottery they might give you one of them. Okay, one of the main paper that is supposed to go for exam generally will have a numerical question from this chapter and not a derivation. But in case they are giving a derivation, there is a high chance this derivation will come. And in case they are giving a numerical question also, this formula still may be important because the numerical question is based on this formula. So this is one of the most important formula from this chapter. So what does it say? It says that 1 by focal length equals to n21 minus 1 minus 1 by r1 minus 1 by r2. So what are those things? Let us understand that. First of all, if the refractive index of this medium is n1, refractive index of this medium is n2, then n21 is obviously n2 by n1. Okay, this is fine. Now what is r1? r1 is the radius of curvature of this surface. r1 is the radius of curvature of this surface. And what is r2? r2 is the radius of curvature of the other surface. Okay, so obviously r1 is positive, r2 is negative for convex lens. For concave lens it will be opposite. For concave lens, the sign convention is very, very important. No matter what formula you are using, if you are using a problem on lens, sign convention is very, very important. So this is r1, this is r2 for a concave lens. So this is negative, this is positive. Okay, and generally they will not cancel each other. They will either add up positively or they will add up negatively. So there will be a negative sign common and you get the value. Okay, for equiconvex lens, r1 and r2 are equal in magnitude wise, but directions are different, so you can write 2 by r directly. For equiconvex lens, this simple formula can be written as 2 by r. Now lens equation, so from that equation you can derive this lens equation. Lens equation is 1 by v minus 1 by u equals to 1 by f. Magnification is v by u. If you compare with mirror equation, the negative sign in mirror equation is missing over here, otherwise the formula is same. Now power of a lens is given by 1 by f. Power of a lens is given by 1 by f. Now remember that in this particular case for P, the f is in meter. Okay, for this last case power, f is in meters. The SI unit for power of a lens is diopter and it is given by 1 by meter, 1 per meter actually. So if the focal length is given in centimeter, then power is given by 100 divided by f in centimeter. This is a shortcut to calculate the power directly. So if suppose they have given a focal length say 20 centimeter and they ask you what is the power, then it will be 100 by 20, that is plus 5. Okay, you don't need to convert 20 into meters then calculate. It is much easier if you use 100 by f. Combination of thin lenses. So now if you keep two lenses in contact with each other, very close to each other, then the combination of thin lenses is given by 1 by f1 plus 1 by f1 f2 by f1 plus f2. So actually 1 by f equivalent is 1 by f1 plus 1 by f2 plus 1 by f3. This is general formula. Okay, if the thin lenses are very thin, if you more than one lenses are in contact, then the equivalent focal length can be calculated similar to that of parallel combination of resistances. Okay, this is a way to find the equivalent focal length. Similarly, power of a combined lens is given by P1 plus P2. So if you are someone who wears spectacles like me, then you have visited a doctor and they give you a special spectacle to wear and then they put up powers. Okay, so 1 power, 2 power, 3 power. Now how does it work? They work in this principle. Okay, so if after one lens they say is it clear, then they will put one more lens and it is clearer or darker or not sharper. Okay, so they ask you various questions. So those who have specs, they know. Those who don't have specs, unfortunately they will not be able to understand this. Anyway, so where there they put more than one lenses on a single side to check whether you are able to see things clearly or not, and that is basically addition of powers. Now next is refraction through a prism. This is also an important concept. So if you see the angle of incidence and angle of refraction, they are related to each other. Now here what we do, we take this as angle of incidence and we take this as angle of emergences. These R1 and R2 we generally do not take. Okay, now this angle of incidence and angle of emergence, they are related to each other through the angle of deviation. This angle is called angle of deviation. What is this? Again, if the ray of light was traveling straight path and after the light bend, so whatever, if you backtrack it, whatever is the angle between these two lines is called angle of deviation. So this is the angle of deviation, delta. Okay, so I plus E, I is the angle of incidence plus angle of emergence, equals to A plus delta. Obviously you can measure I and E, but R1 and R2 you cannot directly measure. You can measure them through some geometry, and from geometry it can be shown that no matter whatever is the I and whatever is the E, R1 plus R2 is always same, and that is equals to the angle of prism. This is called refracting angle of the prism, okay, or angle of the prism, which is given by this value A. This angle is called A as the name. Okay, now at refraction through a prism at the minimum angle of deviation. Now if you plot the graph of angle of incidence versus angle of deviation, what you will observe that as you are increasing the angle of incidence I, the graph appears like this. The graph appears like this, and for a particular case at this point when angle of incidence is exactly equals to angle of emergence, this is a particular case. For each case you are getting one angle of incidence, another is angle of emergence. Similarly, when you are getting this as angle of incidence, this will be angle of emergence. So angle of incidence and angle of emergence are also linked with each other through this graph. Now for a particular case, okay, you will observe that angle of incidence is exactly equals to angle of emergence, and that value is basically giving you a minimum delta. So if you plot this delta value, this is the delta value, right? This is delta value, this is angle of incidence value, this along this axis. So when you plot this, this is the minimum point, so this represents the minimum delta or the minimum deviation. So the light is traveling, light is suffering minimum angle of deviation. This is a very, very important method determining the refractive index of a given material. Okay, so at the angle of minimum deviation, I is equals to E. And obviously because I is equals to E, I and E are equal means R1 has to be equals to R2, and let's say that value is given by R. Then angle of incidence is given by A plus delta M by 2. Delta M is the minimum deviation. Angle of refraction is given by A by 2, and from there you can calculate the refractive index of the medium. This is a method to determine the refractive index of a particular medium. You make a prism out of it, you put it inside a lab, okay, you measure the angle of deviation, and from there you can calculate the refractive index. Okay, we have done it in our physics practicals when I was a student in our graduation classes. We have performed this experiment, and even we have plotted this graph as well. Okay, anyway, you are not doing these practicals, even though it is there in your syllabus in a slightly easier format. A certain prism is found to produce a minimum deviation of 38 degrees. It produces a deviation of 44 degrees. Excuse me, it produces a deviation of 44 degrees when the angle of incidence is either 42 or 62. That means this is the pair. So if this is I, this will be E. What is the angle of incidence when it is undergoing minimum deviation? Angle of incidence will be same, right? So we know that for 44 degree, this is the I and E. We know that I plus E equals to A plus delta. Okay, so now in this particular case, angle of the prism is not given. Angle of the prism is not given. So what is given? 42 is angle of incidence, 62 is angle of emergence, and that is equals to A, which A is not known, and delta is 44 degrees. Okay, so we get 104 equals to A plus 44, or A equals to 60 degrees. So A value, this is a equilateral triangle or equilateral prism. Now we also know that I, for minimum deviation, I is given by A plus delta divided by 2, delta M. So A is 60, delta M given is 38 divided by 2. So it will be 98 by 2, that is 49 degrees. Okay, so it will be 49 degrees. 49 degrees is the minimum deviation. So now let's continue with the lecture, the microscope. So first, now we are basically at the last end of phase of our lecture, where we are going to discuss microscope and telescopes. Okay, so microscope basically is a device which we are using to observe smaller object. Okay, micro means which is smaller in size, and we want to observe them in a bigger size. Okay, so basically it is a device which helps us to observe microbes. Okay, microorganisms or micro objects, both way. Okay, a simple magnifying microscopes are basically, first type of microscope is a simple microscope. A simple microscope is basically nothing but a simple convex lens. A simple magnifying lens or microscope is a convex lens of small focal length. It is used for observing magnified images of objects. The idea is to get an erect, magnified and virtual image of the object at a distance, so that it can be viewed comfortably, that is at a distance 25 centimeter or more. D is equal to 25 centimeter is called distance of distinct vision or near point. So even if you think that if you keep an object very close to your eye, you can clearly see that actually it is not true. The minimum distance to observe something very clearly and with relaxed eyes, then it is 25 centimeters. So that's why it is recommended that you should not bring a book very close to your eye. Okay, because our eye can, even though based on your eye quality, you can still read something which is slightly closer than 25 centimeter even, but that is very, very stressful to your eye. Okay, so you should, if you are watching my video also from very close, then do not do it. You should observe everything at a distance of 25 centimeter minimum. A normal human eye can observe things from 25 centimeter till infinity. Okay, normal human eye can observe distances from 25 centimeter to infinity. That is, this all information we have studied in our class 10th in the human eye chapter. But anyway, just to refresh your memories, so when we are observing a very small object kept on this table, okay, this is a simple microscope, this is a convex lens, simple convex lens. Okay, those who use biology lab, they may know. Okay, this is one of the simple microscope. There is a mirror which reflects the light back to the lens, and through this you can observe the magnified image of the small object. Okay, this has a limited capacity. The magnification is also very, very limited. Okay, angular magnification, the magnification of the optical instrument depends on the location of the final image. Optical instrument right, a simple microscope's magnification also depends on the location of the image. When the final image is formed at the least distance of distinct vision, that is the minimum distance where you can see anything clearly, okay, the magnification is given by 1 plus d by f. D is a fixed number obviously, and f is the focal length of the lens. Okay, so if you are observing from here, so here is the object and you are observing a magnified image. Okay, and the principle that we use is that a simple convex lens, when kept when the object is kept at a distance closer less than focal length, it forms a virtual and enlarged image. Okay, so based on that principle we use convex lens as a simple microscope, right? And the spyglass of Sherlock Holmes is also a microscope. You can consider that also be a microscope. Now let's move on. When final image is formed at infinity, this formula is most important. When the final image is formed at infinity, then the magnification is given by capital D divided by F. Okay, so capital D divided by F is the final image is at infinity. So it is located exactly at focal length. When the object is located exactly at focal length, the final image forms a very far away, and you are supposed to see a magnified image. Even though the magnification is not infinite, it is given by the distance of distribution divided by F. Okay, so as you can see, even the image is very large, you will not be able to see a very large image because of the limitation of your eye, and you will see only a magnification by D by F. Now the microscope is basically an instrument where more than two lenses are used to see an image clearly. Now there are two lenses, one is called objective lens, another one is called eyepiece. So as the name suggested, objective lens is kept near the object and eyepiece is kept near the eye. Okay, eyepiece is kept near the eye. And this combination is called compound microscope. A simple microscope has a limited maximum magnification. For realistic focal lengths, for much larger magnification, we need to use two lenses, one compounding the effect of the other. This is known as compound microscope. So I just wanted to give you a clarity that generally the objective lens, or the lens which is facing the object, is smaller in size. The eyepiece which is facing the eye is generally bigger in size. Also, the first image formed by the objective, is a real and inverted image. So based on this, we have seen more than two MCQs, one in KCET, one is in your board exam as well. Okay, so the objective lens always forms real and inverted image. Eyepiece on the other hand forms virtual and it is still inverted. The eyepiece will still forming a inverted and virtual image, because this image is inverted, so this image will also be inverted. Okay, and it is forming a enlarged and virtual image. Objective lens also forms enlarged image. Obviously the size of the object increases, but it's a real image. Okay, so don't be confused. Final image is virtual and enlarged and inverted. The in-between image between objective and eyepiece is real and inverted and enlarged. Okay, it is real. Only difference is this is real, the other one is virtual, but both are inverted and enlarged. The lens nearest to the object is called objective, forms a real inverted magnified image of the object. This serves as the object for the second lens. So this one is as object for the second lens. Okay, this the eyepiece, which functions essentially like a simple microscope or a magnifier, produces the final image, which is enlarged and virtual. Okay. Both lenses are small focal lengths, but focal length of objective must be smaller than focal length of eyepiece. Okay, so remember this, this image which is forming here, this should be at least on the focus or closer than the focus. So focal length of the eyepiece should be here. So focal length of the eyepiece should be slightly bigger. Focal length of the eyepiece should be slightly bigger than the exact location of the image. That's why it is compulsory that focal length of the objective is less than that of focal length of the eyepiece. Okay, so higher the focal length, so if you are given a two lenses, one is say 8 centimeter, another one is 10 centimeter, then 8 centimeter should be used as objective and 10 centimeter should be used as eyepiece. Okay, so this is also can be asked as an objective question. Now when final image is formed at least distance of distinction, the magnification is L divided by f naught 1 plus d by fe. Okay, L is the length of the microscope tube. The distance between basically L is the distance between objective and eyepiece. This distance is L. Okay. Now when the object is formed at infinity, this formula is more important. When the image is formed at infinity, L by FO, L by objective into D by FE. Okay, L by FO into D by FE. So both focal lenses are in division. Okay, length or the distance between the lenses is L, and D is the distinct vision, which is 25 centimeter. Okay, so when everything is given, you can calculate the magnification of a compound microscope as well. An angular magnification or magnifying power of 30x is desired using an objective focal length 1.25 centimeter and eyepiece of focal length 5 centimeter. The length of the microscope will be, now this is option is wrong, anyway ignore it. So what we have found that 30x, that is magnification, is given by L by FO into distinct vision divided by FE. Okay, so here FO is given as 1.25 centimeter, so L by 1.25, and distinct vision is fixed for any object, so 25 divided by 5 centimeter, and the magnification that we are expecting is 30. Simple calculation, 5 5s are 25, and we get this will be 4. So L will be 30 divided by 4. So it will be 7.5 meter centimeter. 7.5 centimeter should be the length of the microscope. Now remember, in case of a microscope, you cannot add these two values to get the length. Okay, for telescope, if you add the two focal lengths, you will get the exact length. For a microscope, that is not the case. Okay. Now telescope, what is a telescope? Telescope is tele means which is far. Okay, tele means which is far. Telescope is basically an instrument which is if you remember when we are kids, you may have, some of you may have seen it, the channel there was a channel called Doordarshan. It is still there, but it is almost obsolete. No one watches Doordarshan anymore. Okay, so Doordarshan means you are watching something which is very, very far. Dur means Dura, which is far, and Darshan means observe, okay, or seeing. So when you are observing something from very far, that is called Doordarshan. That's why the name called television. Okay, television or TV that we use, right? So television is basically something which helps you to observe which is happening very far away. Okay, obviously it is not happening in your home, but still you are seeing what is happening in the web series or the daily soap, whatever is being watched in your home. So that is something helps you to observe which is very far away. And telescope is also a device which helps you to observe something which is very far away. Now based on the application, telescopes can be categorized into two parts. One is terrestrial and one is astronomical. Terrestrial means if you observe something which is like a Jack Sparrow. Okay, you are observing another ship coming from a distance. Okay, so that is a terrestrial telescope, which is basically used to observe something which is around us. Okay, a binocular is an example of terrestrial telescopes. Okay, so terrestrial telescopes which helps us to observe something which is happening on the earth somewhere far away, but we are observing it using either telescope or binoculars. Binoculars is basically pair of telescope, terrestrial telescopes, and astronomical telescopes is something which we observe distant stars, planets, okay, whatever is moving outside our earth. So if you are using it on the earth, it is called terrestrial. If you are using it for outside objects on outside earth, then it is called not extraterrestrial, it is called astronomical, right? Now in this chapter we are basically discussing astronomical telescopes. It is also a combination of two lenses like compound microscope. Okay, one is called objective and eyepiece separated by a distance. It is used for observing distinct images of heavenly bodies like stars, planets, etc. Because they are in the sky, they are called heavenly bodies. Now if you see that in case of telescope also, we have the objective lens forming a real and inverted image, and the eyepiece is forming a virtual and inverted image. So in both cases, be it microscope or telescope, the intermediate image is always virtual. That is, objective lens always forms objective lens always forms real images. Okay, final image is virtual for both cases. Now if you see in this particular configuration, the size of the objective is much bigger compared to that of eyepiece. The main reason is that the object which we are observing is very far away, so the amount of light which is coming towards us is very, very small. Okay, so we need a large aperture or a very large objective lens, which will basically provide you a lot of light to fall, and then you can focus it using your eyepiece and you can observe it. Clear? Yes, they can be focused as well. Now, similar to that of compound microscope, objective lens of an astronomical telescope forms a real inverted magnified image of the object. The eyepiece produces the final image as enlarged and virtual. Okay. Now magnification, when the final image is formed at infinity, then the angular magnification is given by m equals to FO by FE. In case of astronomical telescope, the final image, we always like it at infinity. Okay, so that we get as much magnification as possible, and in that case magnification is focal length of objective lens divided by focal length of eyepiece. So that means in this particular case focal length of objective should be higher compared to that of objective, exactly opposite to that of microscope. In fact, there is a story, there is a legend, I don't know whether it is true or not. There was some person in Italy discovered microscope. Okay, Galileo, that person who discovered microscope was a spec maker. Spec maker means who used to make spectacles. Okay, he uses two lenses and he observes something which is small objects appears to be larger for him. Galileo borrowed the idea from him and he reversed the lenses and he created the first telescope. I am not sure whether it is a legend or it's a true thing. So basically, if you reverse the order of microscope, you can somewhat create a telescope with some modification, of course. So basically, just reversing the lenses will not only do, there will be some modification, as I mentioned. If you can modify them, you will be able to see distant objects. Okay, and obviously Galileo Galilei is a very famous person. He did a lot of inventions and theory of physics as well, and obviously he discovered moons of Jupiter. He even observed a lot of planets near Earth. Okay, he exactly counted how many moons are there in Jupiter. He saw the ring of Saturn, etc. So he did a lot of research on astronomy as well, right? And the magnification of telescope is given by focal length of objective divided by focal length of eyepiece. Now length of the telescope is also important in case of telescope. So length of the telescope is given by simply adding FO and FE. Okay, note, for larger magnifying power of a telescope, FO should be large and FE should be small. For large magnifying power, a microscope, FO must be obviously, for large magnifying power of a microscope, FO is less than FE. For FE should be small. Okay, for telescope, but for telescope, FE should be smaller, we can say smaller than FO. So this is basically a difference between telescope and microscope. In a laboratory, 4 convex lenses L1, L2 and L3 and L4 of focal lengths 2, 4 and 6 and 8 cm respectively are available. 2 of these lenses form a telescope of length 10 cm and magnifying power 4. The objective and eye lenses are respectively L1. So what is the combination of this we will be using? Okay, so the length is 10 cm and magnifying power of 4. Okay, so magnifying power of 4 means magnification is basically F of objective divided by F of eyepiece. So if you see that only one of them can, only one combination basically can give you that magnification when you put FO as 8 and FE as 2. Okay, any other combination will not give you this magnification. So only 2 and 8 can be given as your combination, and if you add these two also, 2 plus 8, you are getting 10. Okay, so 2 plus 8 is 10, and magnification condition is also satisfied. That means it will be L1 and L4. L1 will be your eyepiece, and L4 will be your objective. So objective and eyepiece, L4, L1. So it will be L4 and L1. L4 is your objective, so higher focal length, and L1 is your eyepiece because lower focal length. So L4, L1 should be the combination that we should use. Now remember, if you see 6 and 4, adding them is giving you 10, but dividing them is not giving you 4. So 6 and 4 combination is not possible. Now refractive telescope. Refractive telescope means where you are using lenses. Big lenses tend to be very heavy and therefore difficult to make and support their edges. So lens is something which is basically working on the principle of refraction. Now refraction means light has to pass through it. Now if you make a very huge lens, you have to support it. Now support can only be provided along the edge, right? You cannot put something in between the lens, then it will block the path of the ray, and basically it will be a useless device, right? So you cannot block the central part, so only the edge can be used. Now bigger the lens, it is using glass, mostly some high quality glass, and because of that the weight of that glass piece is very high. So we generally do not use a very high very big focal length. We cannot create basically refractive telescopes which are able to produce very highly magnified images. Okay, so further it is rather difficult and expensive to make such large size lenses which form images that are free from any kind of chromatic aberration and distortion. Now what is chromatic aberration? So as I mentioned, refractive index depends on inversely with the wavelength of light. So when the light ray, suppose a red light is falling on it, red light having a very large focal length, focus over here, suppose this is red, and a violet light falling on the lens, it is simply merging much before that, so the focal length is much smaller for violet light. Okay, so basically what happens is that you are getting, instead of getting a single object, you are getting different colored object. Okay, so it is very difficult for you to prepare a chromatic aberration free lens. There is one device, obviously if you are someone who used to take pictures in your mobile phone or using your camera, they basically use chromatic aberration free lenses. Mobile phones sometimes digitally correct it. Okay, so after taking the image they digitally process it, so there is a level of processing involved. In case of cameras, digital camera or physical camera, the lens itself is equipped to reduce the aberration. Okay, now then what should we use to observe distant objects? Because distant objects we cannot capture it using a simple camera. Okay, small lens with chromatic aberration free is possible, but big lens with free of chromatic aberration, and obviously size is a matter, weight is more, you don't able to support it properly, so you need a bigger structure. So what scientists have came up with, they are basically came up with a reflective telescope. Okay, reflective telescope basically uses reflection of light rather than refraction of light. So Cassegrain is one of the person, he designed this telescope, okay, where he using concave mirror as well as a convex mirror. Okay, concave mirrors are used to collect the ray. So the ray of light falling on concave mirror, ray of light falling on the concave mirror, okay, and they tend to converge at some point. Now there is one drawback of this system as well. If you are not using this secondary mirror, the ray of light will focus inside the tube. So that is also a problem. You will not be able to see anything if it is forming an image. If you are using a simple concave mirror, okay, you will not be able to see if there is an image or not. So for that what they do, they use a very small secondary mirror, okay, secondary convex mirror, okay, which actually focuses the light back into our eyepiece. Okay, so this is the eyepiece, normal convex lens, and after falling on this light, okay, overall magnification improves, and you don't need a complicated heavily funded design as well, because this is a concave mirror. Concave mirror can be supported from its back as well, because it is functioning on the principle of reflection, not refraction. So light ray do not need to pass through it, so you can provide a proper support to that, so your structure becomes stable, your structure becomes much more easy to observe. Okay, now this is one of the design. The modern Cassegrain telescope does not use this design. There are much more improvement from there. Okay, if you have observed a Cassegrain telescope, generally Cassegrain telescope's back side is blocked, only front side is open, and there is an eyepiece which is mounted on the middle. Okay, so basically there is a concave mirror on the inside that. It looks like a cylinder. Okay, many of you may have seen it. Okay, it looks like this. Okay, but there is no opening on this side. There is an opening on this side through which light is falling, and you see something over here. Okay, in some astronomy exhibition maybe you have seen. Okay, and from here you actually observe the image. Okay, so basically they use a convex mirror over here and prism setup over here. The prism setup actually transfer the light in this direction. Okay, and through that you can see the beautiful images of moon, beautiful images of Jupiter. Okay, there are a lot of other stars that you can observe using this. This is the one of the simplest, cheapest telescope. Okay, so there is no chromatic aberration. First of all, in mirrors there is no chromatic aberration, so the light, the angle of reflection does not depend on wavelength, so all lights reflect by equal angle. So there is no chromatic aberration in a mirror. Mechanical support is much less of a problem, since the mirror weighs much less than a lens of equivalent optical quality and can be supported over its entire back surface, not just over its rim. One obvious problem with the reflecting telescope is that the objective mirror focuses the light inside the telescope tube, but that can be overcome using design. That is a design problem rather than a physics problem. Okay, physics problem means chromatic aberration is a physics problem. Okay, then design problem in terms of lens is also there, but size of the you cannot support it from the only from the support. Okay, that is also a design problem, but here both cases, both problems that we have resolved it. Physics problem is no longer there, and there is only a small design problem. If some designer comes and design it like this way, there will be no problem at all. Okay, almost all the bigger observatory centers that is located across the world, mostly they are built up on mirror setup, not on lens setup. One of the most notable lens setup telescope is Hubble's telescope. Okay, to make it work, it was posted in the space and not on Earth. Hubble Space Telescope, you may have heard about it, which is which has taken wonderful pictures of the space, and that is basically located outside Earth, and the size of the lens is actually not very huge. Okay, it was mainly the post processing after the image is captured that is more important. Okay, you require a lot of post processing of the images captured by Hubble. Okay, now summary: microscopes magnification is given by L by FO into D by FE. Telescopes magnification is given by FO by FE. Refractive telescopes have zero chromatic aberration. Now let's move on to the formula sheet. Formula sheet for the entire chapter is given here. Okay, so here is the formula sheet, and with all the basic concepts. So if you want to revise the entire chapter quickly, you just need to go through the formula sheet, and entire chapter will be revised very quickly, including the formulas, including some basic concepts as well. Okay, now for lenses, formula is there. Okay, even power is mentioned in terms of centimeter. Spherical mirror formula is here. Spherical surface formula is here. Lens maker's formula is also here. Okay, and one more page of telescopes and microscopes. So telescopes and microscopes formulas are also given in this sheet. So if you still have any doubts, any questions, please don't forget to mention that. Don't forget to mention that in the comment section below. Also, to download the PDF of this lecture along with the formula sheet, along with everything, you must join our WhatsApp channel. The link of the Google Drive will be shared on our WhatsApp channel only. I'll be back with a new lecture very soon. Till then, bye.